We summarize the critical point, the type, and the stability of the equation x prime equal to a times x, where a is a 2 by 2 matrix. So we have lambda. We look at the eigenvalues methods. We compute the eigenvalues lambdas of a. So lambda is an eigenvalue of a if determinant a minus lambda I equal to 0. In our case, we have a minus lambda b c d minus lambda. Determinant of this equal to 0. Determinant of this is lambda square minus a plus d lambda plus ad minus bc. So lambda is a solution of this one equal to 0. So we have the sum of two eigenvalues lambda, say lambda 1 and lambda 2 will be a plus d, and the product lambda 1 times lambda 2 is ad minus bc. So the sum is this one and the product is this one. This a plus d is the sum of two entries on the main diagonal. So this is the tray of the matrix A. Tray of the matrix A. In this exercise, we call it T. AD minus BC. AD minus BC is the determinant of A. And we call it D for this exercise. Now, the characteristic equation, this one, equal to 0, can be written as lambda square minus t lambda plus d equals 0. So lambda square plus t lambda plus d is 0. We have quadratic equation delta minus t square. So t square minus 4 times d times 1. So we have three cases here. Bigger than 0, lambda bigger than 0, lambda equal to 0, or lambda less than 0. This one we will have two real eigenvalues. Lambda 1, lambda 2. The second case we have repeated real eigenvalues. Lambda 1 equal to lambda 2. And the last case we have complex eigenvalues. Let's say a plus minus bi. Now let's look at the three cases on this plane. One is the tray axis, and the other one is the determinant axis. Tray and determinant. Now let's look at this. Let's look at the case where lambda, we have two repeated eigenvalues lambda, or delta equals 0. Delta equals 0, t square equal to 4t. Delta equal to 0, t square equal to 4t. Or in the usual case, we know that the equation d equal to t square divided by 4. So it's like y equal to x squared divided by 4. It is a parabola. If you think of that as x, the other one is y. Parabola, this one. So let's say this curve, this graph represent for the point where we have delta 0. So for example, on the curve, for example, this point is correspond to d equal to t squared divided by 4. Assume that I have a bit higher determinant, right? But the trace is still the same. So this one would give us the point, say, d bigger than t squared divided by 4. So what does that mean in this case? So 4 times d bigger than t squared. So this one's is negative. So the point in this region correspond to delta is negative. And the point on this region or anywhere here. So for example, this one, you have the points correspond to d less than t squared divided by 4, or t squared bigger than 4 times d. So this corresponds to delta bigger than 0. So for every point below this parabola, delta bigger than 0 here. So here is the region where we have delta negative, which means that we have 2 complex eigenvalues. And all of this region correspond to delta positive, so we have 2 real eigenvalues. Let's look at the region, the lower half plane. For the lower half plane, let's look at this first. For this region, we have determinant is negative. Determinant is negative. So first of all, this one we have two real eigenvalues, lambda 1 and lambda 2. They are distinct. So lambda 1 different from lambda 2. That's the first thing. Second thing, we know that determinant, or in this case we call d, is negative. D determinant is a product of 2 eigenvalues. Lambda 1 times lambda 2 negative. This means that the lambda 1, 2 has opposite size. Opposite size. So one positive and one negative. So this one would give us saddle point. The critical point 0, 0 of the equation, the differential equation we look at, will be a saddle point. And saddle point is unstable. So this means that in the lower half plane, we know that it is a saddle point. So the picture we have would look like this. Yeah, everywhere here. Now let's look at this region. We know that we're still in the case delta bigger than 0. Delta bigger than 0. We still have 2 real eigenvalues, lambda 1, lambda 2. Number 1 is different from lambda 2 and they are both real. We know that a trace is negative. So this size corresponds to negative trace. And the determinant is positive. So lambda 1 plus lambda 2 the trace. is negative. Lambda 1 times lambda 2 is positive. So they have the same sign and the sum is negative. So this means both of them, lambda 1 and lambda 2, must be both negative. So the product is positive. Negative times negative is positive. The sum is negative. So each one of them must be negative. For this we have, so there are two cases. They can be so they are negative, so they are distinct, and therefore we have a sink. So for example, we have two eigenvectors because we have two eigenvalues are distinct, so we have two linearly independent eigenvectors, and this is a nodal sink. So from, let's say, from one direction, when t tends to plus infinity, is go like this, and this minus infinity, it could be something like this. If we zoom close to here, is follow this one of the eigenvectors line. Improper nodal sink. And we do similar, we can have improper nodal source in this case. Look at this region. So for this region, we know that we have two distinct eigenvalues lambda. Lambda 1 is different from lambda 2. The determinant is positive. The product is positive. Lambda 1 and lambda 2 must be of the same sign. The trace is positive, so the sum is positive. Lambda 1 plus lambda 2 positive. So we know that they have same sign and the sum is positive. Both of them must be positive. So in this case, the picture will look like this. Assume that we have two distinct eigenvalues must correspond to two linear independent eigenvectors. And because they are positive, so it go off infinity here. So the pictures could be something like this. Improper nodal source. Improper nodal source. And this case is unstable. Yeah, I should note the other side is must be stable here. This one. So the point on this one correspond to delta is negative. So we should have a plus minus b times I. Determinant is positive, and the trace is the sum of two eigenvalues. So this means a plus b times I plus a minus b times I. So we have the sum is 2a is the trace. The trace is 0 because we are on this line. So this means the real part of the eigenvalue is 0 equal to 0. So the real part is 0. So on this line, it corresponds to pure imaginary eigenvalues. So this means that it has to be the center, the critical point of the system A x prime equal to A times x is a center. So let's draw one example. So look like this. We have ellipse around that, either clockwise or counterclockwise. Now let's look at this case. I say this half. Let's use this. We are here. If we are here, we know that we have A plus minus BI, and A is non-zero. So real part non-zero is complex. We have two conjugates, right? A complex eigenvalues and the conjugate. It should be spiraling. We have spiral point and A. The trace is negative. This means that the trace is sum of two eigenvalues. In this case, we know trace 2 times A is negative. A is negative. So this means that it will e to the at will tend to 0 when at tend to infinity. So this means we have a sink, spiral sink. So the picture there would be something like this. This spiral sink asymptotically stable. The other half, this half, we do similar. The trace is the sum of two eigenvalues. So 2 times A is now positive. 2A is positive. A is positive. So this means we have spiral source. It is unstable. So one example, we draw that, we go up in infinity. We can go clockwise or counterclockwise. So that's for this half. Now let's look at the point on this line. It corresponds to the determinant is 0. So the matrix A is singular. It's not invertible. So in this case, we have 0 as an eigenvalues on this line. Zero as an eigenvalue. So we have eigenvalue 0 and the other one lambda, say lambda 1. 0 and lambda. Lambda here is real negative. So 0 and lambda are negative. So let's say we have two eigenvectors. V1 correspond to 0. V2 correspond to lambda. The general solution xt C1 V1 is lambda 1t 0t, so times 1. C2 V2 e lambda 2t. So see that when t tend to infinity, this one tend to 0. This one tend to 0, so everything goes to this line, V1. So V1, let's say V1 look like this, give us this line, V1. The other one, V2 here. Remember that when these tend to infinity, this one tend to this line. So we have look like this along this line, and on the other solution could look like this. Parallel to V2. And extend to points leaving on this V1. The other side you do the same. It should be like that, but opposite direction. So this case still a sync. It's still sync to 0, but 0 now is not an isolated critical point anymore. Still it's a sync. The other side will look like this. We have V1 and V2. V1 give us this line, V2 here. General solution C1 V1 times plus C2 V2 is lambda 2t, but this one go off infinity when t tends to infinity, and when t is negative infinity we already have this, so everything go outward from that, parallel to V2. For this 0 repeated, then you have two cases. Either this is complete or this is defective. If it's complete, it's just 1 point. If defective, we have parallel lines. In this case, V1, everything's in parallel to V1. Okay, on one side go to this direction, so V1 assume that it look like that. The other side is go opposite direction. We need to look at the case where delta equals 0. We have repeated eigenvalues. One side trace negative, for example, at this point trace negative. Trace negative, for that repeated lambda 1 equals lambda 2. So lambda 2 times lambda must be negative, so lambda negative. And now we have two cases for that. Either it's complete, lambda complete, negative complete, or defective. If it is complete, we have two eigenvectors v1, v2. The complete eigenvectors v1, v2. So the other just sync to the origin. So in this case we have proper sync, proper nodal sync. And the defective case, for the case lambda is defective, negative here, we have one eigenvectors and one generalized eigenvectors, general solution of this form. So v1 give us this line, v2 give us this line. The other solution would be like that's parallel to v1. Parallel to v1. But then lambda is negative, so we sync. Improper nodal sync. Improper nodal sync. And the other side, if we are here, it will correspond to two cases before, either a proper nodal source or improper nodal source, or like that, proper nodal source, unstable, or improper nodal source. Unstable. therefore the point leaving here, somewhere here. This one stable, asymptotically stable. In this case,